If H is a subgroup of G, and we know a representation of H, we can turn that into a representation of G by making a big block matrix where blocks correspond to the different cosets of the subgroup of the big group. That's called an induced representation. So let's let H be a subgroup of a group G. And let's let rho be a representation of H. And let's say that H has index L in G. So there's L different cosets of H and G. So let's let rho be, let's say, an m-dimensional representation of H. So we use this to make m by m matrices for all the elements of H. And there is a ml dimensional representation of G made of L squared, a block matrix, so it consists of L squared m by n blocks. And it's called the induced representation. Rho, we write up arrow, H down here, and G up there. So to do this, we need one representative of each coset of H. So let's let T1 through TL be a transversal of representatives of cosets so that T1H union T2H dot 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 TLH equals G. So we've got the disjoint union of cosets. Their union is G, and any two of them are disjoint. So then we can define the induced representation rho from H to G to be the homomorphism from G to GL LM by setting the induced representation applied to an element little g of the big group to be this block matrix where the blocks are rho, let me say rho hat of T1 inverse G T1, rho hat of T1 inverse G T2, and then finally row hat T1 inverse G TL. So we're almost conjugating the G's, except, well, on the diagonal we are conjugating, but in other positions of this block matrix, we're multiplying by one transversal element inverse on the left and then another transversal element on the right. So then the second row is going to be row tilde T2 inverse G T1, row tilde T2 inverse G T2, etc. up to row tilde T2 inverse G TL. And finally, the last block row looks like row tilde, I'll tell you what the tilde is in a second, TL inverse G T1, row tilde TL inverse G T2, and finally row tilde TL inverse G TL. Now if I put row there, it would almost be a good definition, except row itself is a representation of H. So it's only defined on elements that belong to the subgroup H. And sometimes when you do this funny conjugation, you get something that's not in H. So we'll say that row hat is going to, row hat of an element, let's say G, well there's already a G here, row hat of H equals row of H. I think I don't have enough space to write it down here. Where row hat of H equals row of H if H is in the subgroup, and it just equals 0, the 0 matrix, if H is not in the subgroup. So some of these blocks here are going to be honest-to-God representations of elements in H. That is, if this product of three elements ends up being in the subgroup. And then the other blocks are just going to be zeros. So let's do an example of that. Let's let G be the symmetric group, and let's let H, the symmetric group S3, let's let H be the subgroup generated by S1, so just the identity in S1. And then the cosets are going to be H, S2H, and S1, S2H. And let's let rho be the trivial representation that sends every element to 1. Then if we induce rho from H to G and apply that to, let's say, the transposition little s1, then we get rho hat. Now the first, oh, I didn't write down the transversal, but the transversal, maybe it's obvious, is E, S2, S1, S2. So here we're multiplying by E inverse on the left and E on the right, which is not doing anything. So we have rho twiddle of S1, and then rho twiddle of E on the left and S2 on the right, S1, S2, and then rho twiddle of E on the left and S1, S2 on the right. So S1, S1, S2. Then in the second row we have rho twiddle of S2 on the left. Now S2 inverse is just S2, just like E inverse was E. We're going to have something different in the third row. So S2, S1, E, row twiddle of S2, S1, S2, row twiddle of S2, S1, S1, S2. And then finally, row twiddle of S1, S2 inverse. So S2, S1, S1, E, row twiddle of S2, S1, S1, S2, and row twiddle of S2, S1, 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 S2. All right, now each of these blocks is either going to be 1 if what's inside the parentheses belongs to the subgroup, or it's going to be 0 if it doesn't. So S1 certainly belongs to the subgroup, so the trivial representation maps it to 1. S2, S1 does not, and this is S2. That does not belong there, so we just get 0. And then in the second column, S1, S2 does not belong to the subgroup. S2, S1, S2 does not belong to the subgroup. S1s cancel, S2s cancel. This is the identity element. So that gets mapped to 1 because it's part of the subgroup. And then in the third column, S1s cancel, S2 is not part of the subgroup. S1s cancel, S2s cancel, and we have the identity element. That is part of the subgroup. And then here, 2 S1s cancel, and we get S2, S1, S2. That element is not part of the subgroup, so we get a 0 there. Now if rho has character chi, then we write chi up arrow hg for the character of rho up arrow hg. Two important cases of that are write epsilon lambda for the sign character induced from the Young subgroup S lambda up to Sn, and we write eta lambda for the trivial character, which is what we just did, induced from S lambda up to Sn. So these are just shorthand names, so we don't have to write all of the arrows in two different groups every time. And as we let lambda vary, the characters eta lambda, as lambda varies over partitions of n. This is a basis of the trace space script T of Sn. And then if we take the induced trivial characters, those form a basis also. And maybe you remember that the irreducible characters form a basis also. So now we know 3 bases at least of the trace space of Sn. Well, 4, and let me mention the other one. So we have this indicator character that, well, that's not a character. So we define psi lambda of W to be 1 if the cycle type of W is lambda and 0 otherwise. So that forms another basis. So we know 4 bases of the trace space of Sn. The end.